and welcome to the new episode of the series Building an Autonomous Robot from Scratch, where we are building our Perceptron bot, this little guy here. And in this episode, we will be starting the low-level development, and by this I mean developing the motor drivers, a motor controller, and a serial protocol. And in this episode here, we will be developing a motor driver, which will communicate with the L298 and motor driver, okay? But before we start, I would like to show you how to use PlatformIO IDE, which is the IDE or the IDE we will be using to program the code for Arduino. You might also want to use Arduino IDE. They also have one, but I just think that VS Code is the most used test editor, and they have PlatformIO. So yeah, if you have already programmed before in PlatformIO, just skip this part. This is merely me showing you how to create PlatformIO project. And so yeah. So in VS Code, you just go to the extensions and you search for PlatformIO. This, not like this, sorry. There we go, and you just install this one. And once you have installed, you might need to restart, but once you restart, you will see this little guy here. And yeah, once you have this, you just create a new project, and you open a new project, and you just name test, and then you need to select the board. So I'll be using the Arduino Nano, which is the one I have on the robot. Now, if you are using the same board, there are two main bootloaders. There's an old one and a new one. If you go for the one I have on my list of items, you will have the new bootloader. If you have an older version, then you have the old bootloader. If you don't know what you have, you just select one, and then once you build the project and you try to publish or to push the code to the board, you will get a message error saying that you doesn't recognize or something like this. If that is the case, then you just change to the other bootloader. So yeah, if you want to change, for example, so this is the file structure. You have a platformio.ini, a source folder where it's where all your executables will be, basically. A test folder which we are not using. A lib folder is for external libraries you want to use, for example your own. The include is where all your other files are. So this is pretty much just C development, right? So yeah. So in case you want to switch the bootloader, you can come to the PlatformIO ini. If you have the old one, you just need to add here new, and then here new as well, or the opposite, just remove the new. I am not used to this. Okay. So yeah. Now let's just create a simple Blink program, and I advise you, every time you start a new PlatformIO project, just write the simple Blink LED, because then you will know that everything is working as expected. And if you don't do that and you start developing something and then you try to push and it might not work, it could be that it's some problem with your own OS or something, right? So yeah, so what you need to do is you always need to include Arduino. You always need to have the setup and loop in the main .cpp, okay? So the setup here is just a one-time call by the I guess the bootloader. I'm not sure how it works, but this is called every time you boot up your Arduino, so you can use it to set up things. And then loop is the function that is called in every CPU tick, pretty much, okay? And so to create a Blink program, you just do pin mode. You will select the pin and you will give it what it should do, and usually you have a built-in LED on your board which you can get the pin number by using the macro LED built in, and the mode we want it to be output. What we want is the pin to output something, okay? And once you have this, you just go to the loop, and then now we say digital write. The pin is again LED built in, and we want it to be high. And what this means, well, it means that the pin where the LED is attached, it will be switched on pretty much, okay? And then we do a delay of 1 second, so the delay works in milliseconds, while 1000, and then we do again the same thing, but this time you do a low, so you want the LED to be turned off, and that's it. Once you have the code, you can go here down below. You have these helper buttons, so you can build. Okay, it just compiles everything, and then you can upload to the board. And now if you just click on upload, it will build before uploading, okay? And so here, if you have the wrong bootloader, you will have a message error somewhere here, okay? And yeah, once you have that, you will see on the board, you'll see this red LED blinking, right? And so yeah, that's a nice test. Now, if you're using Linux, and you will be needing Linux for the ROS part, if it's the first time you are doing this, you might get some udev errors, and you need to basically, you need to allow the USB ports on Linux, something like this. If you search on the internet and if you have these problems, there are plenty of tutorials on how to solve this. So yeah, just check them out. But yeah, without further ado, let's just get started with the main thing. Okay. Now I will ditch VS Code because I will not be using VS Code. I will be using NeoVim. And so since I am using only terminal, I am using the PlatformIO CLI application. And so you can just write PO and then yeah, all the commands you need. If you are also using NeoVim or any text editor that does not really support PlatformIO, you can also do this command, compile db, and what this will do is it will generate a compile underscore commands.json, which will tell your LSP pretty much your Clang D, where all Arduino files are located on your system. So we'll create this compile commands file, which is the bunch of paths to all the different files. Okay. So I have already created a empty project in the Perceptron bot GitHub. You can see here on the low level and motor controller. So I have created a different GitHub repo just for this. So yeah, this is the Blink program, the one we have just done before, as you can see. So yeah, you can either way just clone this or make your own Blink program as you wish. Okay, so first thing we want to do is to create a configuration header file, okay? And this will help us kind of on the go, or not on the go, but easily configure, for example, all the pins, PID values, and so on, okay? And we just want to go to the include folder, create a file. I will call it configuration.hpp, and then we want to do if not defined configuration underscore hpp, define configuration. I'm using GitHub Copilot, so that's why I have this compilation thing. Just makes life easier. And so I have already here basically what we will need. So we need basically the motor pins, okay? So I do have it here on my second monitor. You can also get it this once I push. So what do we have here? So if you have watched the previous video when connecting things, I have showed you this thing. And this is where you will need to plug everything pretty much to the Arduino. So ENA, IN1, IN2, ENB, IN3, and EN4, these are from the L298N driver. And then this is for the encoders. Now, something you need to be careful, if you don't choose these pins, you will need to make sure the ENA and ENB pins are in a PWM pin, right? That it supports PWM signal. And that the left encoder yellow wire, also known as phase A, and the right encoder yellow wire, they need to be plugged into an interrupt pin. All the rest, you should be able, they need to be a digital pin, not an analog pin, okay? That's all you need to know. So yeah, if you don't go for these pins, be careful. And so that's basically what I have here. So I have that motor right, EN, right, is to pin 10, and then IN1, IN2, 6, 7. I basically just mapped these values to micros, okay? And so yeah, that's pretty much what we need for now. Nothing much. And so let's just create now a motor driver.hpp, and here as well a motor driver.cpp. Okay, so I like to always declare if not defined motor driver, and then define motor driver. And what this will do is it will prevent the compiler to basically include this file multiple times. And this will optimize the compilation time. Not for this, it will not really matter because this will be a small project. But for larger ones, you definitely want to have this thing. Or even Pragma ones, which is a newer GCC thing. So we want to include definitely Arduino. Okay, this will have everything that is related to Arduino, like the pins and so on. And we don't really need configuration for now. So we want to create a class, motor driver. And here we want a public and a private. So if you have never programmed in C++, I advise you to just go through a quick tutorial just to get a bit familiar with. If you have programmed like Java or something like this, it will be most likely resemble a lot, but yeah, it's not the same thing. So in public, you want to create a motor driver. Oh my god. And yeah, so let me get my code I did previously. So let's start with the attributes, okay? We will need a few. So so we need to define the pins, and the pins we'll need to define are the L298 driver pins, okay? So we want uint8, yeah, pin UAN, so the PWM signal. We want uint 8. God, I am very slow today. Pin IN1, and I like to put an underscore at the end to tell you it's a private attribute. T pin in 2. So these are the pins we need. Now the pins for the encoder, they will come later. Additionally, we will need some parameters like the wheel radius, how many ticks per revolution the encoder does. And so for the wheel radius, we will need a float value, radius. We will need also a ticks per revolution. I will use an integer, not an integer, sorry, uint 16, because it will always be positive, so no need for having an integer. So ticks per rev, I guess. Yeah. What else do we need? We need a flag reverse. And what this flag means is, so we have the right and left motor, right? And for example, the right motor, you don't need to reverse because it will turn in the right direction. But in the left one, if you do not reverse the directions, it will think the forward direction is actually going backwards. So that's why we need this reverse, so that we can reverse the motor driver to go forward instead. So that's all for like parameters thing. Okay. And now we need some like sensor readings. Okay. We don't need the ticks, but we need so we need to create some structures here. So class, actually no, first of all, let's create type define struct, and then motor, what did I call it? Motor data. Okay. Missing an E here, there you go. And then we need a float velocity, float PWM, not PWM, sorry, angular velocity. We need a float distance, and we need a float angle as well, yes, and a float RPM. These values will, or these variables will make sense in bits. So one thing I haven't yet specified is that we have two types of motor drivers. We have, or maybe there are more, but I only know two. We have a closed loop motor driver and an open loop motor driver. Now, what are the differences? The open loop, it means that it doesn't really know how fast it's moving and how much it has traveled, what the speed is, and so on. And in our case, it just means that you specify a PWM value, let's say 100, and then the motor just runs at this PWM value. But we don't really know anything about the motor itself. How is it moving? How fast is moving? And this is not what we want for ROS purposes, because we want to know how fast the motors are moving, right? Or in this case, how fast the wheels are moving. And now the closed loop motor controller, it knows all of this. So it knows the velocity, the angular velocity, the distance it has traveled, the angle, the RPM, and so on. The way it knows this is by the encoder values, okay, the encoder readings. So the encoder, it will give us, so like I have here a thing. So if you don't really know how an encoder works, usually you have two phases, and in our case it's magnetic. It's a magnetic field, and in here we have basically a how does this? What's the name of this graph? I don't know. Basically, we have here a 0, we have here 1, 0, 1, 0, 1, right? This is the PWM signal, pretty much. And so if you rotate, the two phases, they are basically shifted 90 degrees, right? And so we have a phase A, that once it starts rotating, the other one will only basically tick after 90 degrees. And so the way we are working is the phase A is attached to an interrupt pin, and in every rising edge, so whenever the voltage goes from 0 to 1, so here we have this interrupt routine service that will basically get called. And once we do this, we check how is this phase B, what is the current voltage, let's say, where is this graph? Well, in this case, in here, for example, we know that the phase A is in the rising edge, so we have a value of 1. And then we look at phase B, well, it's in the 0 voltage, right? It's 0. And what does this tell us? Well, it tells us where the motor is turning, what is the direction. Here on the bottom, we have the same case, but then the phase B is actually at 1. So when you have 1 and 0, I think this is clockwise, so you are turning clockwise, and this is counterclockwise, sorry, or the opposite, I don't know anymore. Yeah, I think this is clockwise and then this is counterclockwise. Either way, we can see that later, I'm not sure anymore. Either one of these. And so basically that's how we know how fast or how much ticks the encoder has done. So it depends on your motor, your encoder, but one wheel turn, a full 360 degrees, might, I don't know, this one I think it's 400 something ticks. And so if you know this value, well, yeah, then you can compute the RPM, the velocity, the distance, and so on. And that's what we will do. But first, we will just implement a simple open loop motor driver, right? But I will be adding here all these attributes so that we have them for later. So we'll need a motor driver, motor data, and maybe even motor data, like so. We will need as well an int 32 for the encoder, so the last encoder reading. See, I love Copilot, it just helps you very fast. And we need unsigned long last data reading time. So this is for then measuring how fast the motor is moving and the velocity and so on, okay? Right, so I think that's all. Not really. We still need one more thing. We need another class enum motor direction. There we go. This is what I wanted. What did I do wrong here? Oh, it's the opposite. Enum class. And we also actually need an additional stop. So to know that, okay, we are moving forwards. Actually, I don't want to be forward. I want to be clockwise and counterclockwise. I think it makes more sense for the motor. So yeah, we have this, and then we have then the motor direction equals then to a variable like this. Maybe like, yeah, let's shorten this to there. And yeah, okay. So we are almost done for the open loop. What we need is to then create a constructor for this and some functions. Okay, so our motor driver, it needs to know a few things. So it needs to know what are the pins. And yeah, that's pretty much it. So uint 8 pin, there we go. We don't really need the wheel radius because we are not using it. And we need the bull reverse, yeah. We can set this as a default value to be false. Okay. So this is for the open loop only, okay? So what are the functions we will need? We need a function to set the PWM. This will be an integer PWM. Why? Well, we can pass, so a PWM value usually goes from 0 to 255. But since we want to drive the motor both in clockwise and counterclockwise, we will accept a range of values from -255 to 255. And so then we will set the direction ourselves. We want a method run. Now this method will need to be called in every loop of the Arduino. We will need a, I mean, we don't really need, but it's also nice to have a print status method so that it will print, for example, well, in this case, it will not print much. Yeah, okay. This is for later, actually. So that's that. What we need more, let me see. Yeah, in terms of public, it's all. Now we want to also have private ones, so we want to have, oh wait, it's missing something. We're missing something here. We are missing exactly PWM, and actually PWM is uint 8t. There we go. So what we want is a void send PWM. Don't need to have because we will be using the variable or the attribute PWM. We will need a function, a method, sorry, set direction. And here we need to pass the direction. What else? What else? Yeah, one function init pins, so that we will initialize the pins. And I think that's all we need for now. Yeah. Okay. So let's go to our motor driver CVP now. we will then hashtag include motor driver. Okay. And now we will start to define everything. So motor driver. There we go. I will just use Copilot. So what are we doing here? We are saying, so we have the parameter, sorry, and here we are initializing the attributes with the parameters. That's all. Then we are calling the init pins. Yeah, that's good. So now we have void motor driver init pins. And now there we go. Okay, so this is basically what we did with the LED from the Blink program. We take the pin number and we specify this to be an output pin. Okay. Cool. Now we need a void set PWM. Now this is not correct. Okay. So here we need to do some things first. We will actually need first. I shall create another file, another folder, another file actually, utils.hpp, and let me just get what I have here, because you will see what this is. HPP. So what this is are just bound methods, or functions in this case. So we just pass in a value, a minimum and a maximum, and this will bound the value to be always in between min and max. Okay, that's all it does basically. So we first want to do is bound. First we need to also include here the utils. So we want to bound the PWM value to be a 0 between -255 and 255, okay? That's the first thing we want to do. Then, so if the PWM is less than 0, there we go, it does this. So we say that the direction will be counterclockwise, this will be clockwise, and if it's 0, it means you want to be stopped. Okay. Cool, all good. Now we only need the motor driver dot set direction. Here we need the motor direction here. Okay, so now here we have to go to my notes here. So the motor driver has 3 pins per motor, right? We have the EN1, IN1, and IN2. EN1 is for the PWM. IN1 and IN2 will be 2 bits that you can specify to switch the direction of the motor. And these are the bit combinations. So if you have 0, 0 or 1, 1, the motor will be stopped. If you have a 0 and a 1, you will have a counterclockwise rotation. And if you have a 1 and a 0, you will have a clockwise rotation. And now what we need to do is basically just that. So the thing is, we have the reverse, okay? And to be cleaner, what I will do is I will create 2 bytes, IN1 and IN2. And I will be doing an XOR logic gate, basically. Or I will be using an XOR logic gate. So I will call the reverse Then notice that I forgot the underscore on the reverse here. So we have the reverse, and then what we have, well, we do an XOR, exactly this. Let's just copy this. And instead of clockwise, we have a counterclockwise. Okay. And now here we just do a switch. We take the dir, okay. And then we do a case of a motor direction C, yes. There we go. And then another case, which is a default digital lights, like so. So what do we have here? So let's say the reverse is set to false, and the current direction is clockwise. Okay. So this thing here will be true. Okay. And the reverse will be false. So we have 0 and then a 1, and meaning that IN1 will become 1, so high. And so IN2, this will be 0, this will be also 0, and that turns into be also 0, so low. And so here on the clockwise case, we have a high and a low. Okay, if you go back here, high and then low, 1, 0. That's exactly what we have. And then here it does the opposite. So in case this is counterclockwise, this will be set to 0. This will be set to 0. So IN1 is now 0 or low. And this will be set to 0. This will be set to 1. So in the end, we have a high. And this then is low and high. So that's basically it. Otherwise, you will need to have if statements, if reverse, do this, or else do that, okay? And by doing an XOR operation here, you can easily reduce the lines of code. Now, I just want to verify that I am correct here. Yes. Okay. I mean, you could also say that it's a case of motor direction stop, but it doesn't really make sense because it's the only one left, and that's the default you should want to have, right? Okay, so what is there missing? Send PWM, right? So void motor driver send PWM. And the PWM, you just want to take the PWM value and send it to the driver via a PWM signal. And the way you do this, you have a function called analog write. Then you need to pass the pin, which in this case is the N, and then the PWM value, okay? Now this PWM value is set when you call this set PWM, okay? And we make sure that the value is always between 0 and 255 because of this. Okay, so missing only one function, the motor run. Okay, so in this case is only the send PWM because that's all we want to do. Okay, let's go to the main file now. So yeah, this is a Blink program. Now we don't really need it anymore. So first of all, we will actually include the configuration, and we will include the motor driver. Okay, and now we will need to create a instance of our motor driver. So motor driver motor. Can we? Yeah, we can. So I will be using the left motor because it's the one, it's facing me pretty much. So left, oh, is it motor? Left, yeah. EN, motor left, IN1, motor left, IN2, and then the reverse, I will set it to true actually, because since it's my left one, we need to inverse, okay? Okay, now we have the motor here, and essentially, that's all we need. We just need to call motor.set PWM to be 255. Actually, it will be called here in the setup function. And here we just do motor.run. That's all. That's all we need. And so hopefully, if I build, so you can use, if you're VS Code, you can just use the buttons on the bottom. I will plug this into the USB cable to the robots, and hopefully it will upload. It would be good if I have it plugged into my PC as well. Okay. There we go. And let me plug in the robot now. And boom, the motor is rotating. I don't know if you can see something. There we go. So pretty cool. It's working. And now, for example, if we can set this to a, I don't know, 50. Upload again. And now it's rotating slowly. Cool. All we need. So at this point, we have what it's called then an open loop motor driver. Okay. Cool. But for our case, this is not very useful, is it? We want to know the distance it has traveled, the wheel have traveled, how fast it is going, and all of this. And for this, we need an encoder. So I could just very well go to the motor driver and implement here an encoder, encoder logic. But I think it's better to just create an encoder class just for this. Now, be aware that there are libraries already written for this, but I think it's fun and nice to learn by doing things. And that's the reason why I am doing all of this from scratch, pretty much. That way you can learn more things, you can play around with it, and you will have bugs, you will have to fix them, and so on. I think that's the fun on it, okay? So we create an encoder file.hpp and then an encoder.cpp. Okay, so again, if not defined, and then we call this encoder underscore hpp and define hpp. There we go. Oops. So what we need here, do we need Arduino? We might need encoder public private encoder. So what does an encoder need? It needs a phase A, a phase B, and that's pretty much, well, all it needs, right? Let me get my encoder file that I have on my second monitor. Exactly, that's all we need. Okay, so we need a uint8 pin A. It knows. And then, yeah, that's all. Yeah, we also need a Boolean variable reverse for the same case as the motor. So if we reverse the motor, we also want to reverse the encoder, because then, let's say you reverse the motor, but then you don't reverse the encoder values will be negative when it should be positive. So we also need this reverse here. We need a void init pins. We need a get ticks. We need a let me get here. We need the reset. We need a set reverse, yeah. And what else? Yeah, we need a void tick ISR. And what this is, this ISR, is the interrupt service routine. And basically, at least in Arduino, when you set up an interrupt pin, you will need to pass in a function. But since we have this function here on the encoder, we can't really set up ourselves here on the encoder. We need it to do outside the encoder. And that's why you have this tick ISR function method. Yeah, that's all we need. Now let me put this as a private method. Okay, so now what we need is, let me see, we don't need this. We only need pin A, pin B, we need the reverse, exactly, and we need the ticks. Now the ticks, in 32 is okay, because, okay, I have it, on my thing I have it set long. I think it's the same. Let me just check. Int 32. No, so long Arduino size. So it's 4 bytes. So it's a 32 bits exactly. Okay, maybe it's easier to see what this is then. The reason why we have volatile is since this will be updated only here on the tick ISR pretty much. The compiler, when compiling, it will see, oh, this is not being used, so it might just ignore this and just not include in the code. But we want this to be there, okay? That's the reason why we have this volatile. It will tell the compiler to not mess around with this variable, just let it there. That's all it does pretty much. Okay. So this done, we have the encoder. So include encoder, and now we don't need this, no. So we have encoder, uint8 pin A, uint8 pin B, bool verse. There we go. So I forgot something, guys. Oh no, never mind, it's there. Bool reverse to set to false as a default value. So again, we initialize pin A, pin B, and reverse, and the ticks as a 0 value. So let me remove this. Init pins, yes. Then we have the encoder. Void resets, and that's all it does exactly. Void encoder get ticks. Now here we will do something different. We will say so int 32 ticks equals 0. Then we will call this atomic block. This is an atomic block. And then ticks, or actually the opposite, ticks equals ticks. And then we, oh yeah, this is actually not the void, but an int 32. So let me change here, int 32. And then we need to return ticks. So why did I do this? Oh yeah, sorry. So we will return, actually reverse ticks. So if it's reverse, we say minus ticks, else we just say ticks. So why did I create this atomic block? So it might happen that you are turning the wheel, and so no matter what, when you have an interrupt pin, if it detects it's rising, in our case, it will call this the ISR method here. But it might happen as well that you are currently reading this. So let's say you are here on this line, the tick will, the ISR, the interrupt will be triggered. So it will go through the ISR block. It will increment the ticks, right? And then it will be back here, right? And it might be that the ticks will be not the correct ones, okay? So what this does is, when you enter this atomic block, even if you have a tick, you will get the value, the correct value. I don't really know how to explain this, but it's something like this. And then here we have an inline if statement. So we are checking if we have the reverse set to true, then we will invert the ticks, right? So if it's the current ticks are negative, we'll just invert them to be positive. Otherwise, we just return the ticks. Cool, that's all it does. So we have a get ticks, resets, and then we also need then a void encoder tick ISR. And here what we need to do is, if now we need to read digital reads, the pin will be pin B, this one, is equal to high. Does this. So it actually, it's the opposite. Minus minus plus plus. Okay, so going back to the graph here. So we have so when it's 1 1, it's going on the counterclockwise, and if you have a 1 0, you have a clockwise. Okay, so I was correct. It's clockwise and counterclockwise here. Okay. I think that's all we need for this one. Oh no, never mind. We are missing the void encoder init pins. And this is, there we go. So this is all we need. Okay, we need to now set the pin modes to be inputs, because we actually want to listen to things and not output things, right? That's the reason. And yeah, actually I even have a pull up here, input pull up. I don't think it really matters in this case, but it just tells you yeah, input pull up, it means that it is using the internal resistors of the Arduino. So yeah, that's all for this, I think. 1 2 3 4 1 2 3 4 5. Wait, we are missing one. 1 2 3 4 1 2 3. Oh, it's missing the set reverse. Okay, so we have here void encoder set reverse. There we go. Pull encoder, then set reverse. Reverse. There we go. Okay, so that's all we need for now. So let's go now to the motor driver again. So now we will be developing the closed loop version, okay, on top of the open loop. For this, we need to make sure we know in which mode we are. And for this, we will create a class motor mode, open loop, there we go, and closed loop, okay. Now we have this constructor here. And this constructor, we will modify it so that, oh, first of all, actually, we need to create an additional attribute for now. Motor mode, exactly. So when you initialize this closed loop, what you do is just say motor motor mode is equal to motor mode and then open loop. Okay, so now we know, okay, this motor driver will only be working with closed loop motors. You will not be able to switch between open loop and closed loop because that's not possible. Okay. Something we need to change now in the run method. Okay. We will need to make a switch case. Why? We need now to, okay, when running in open loop and closed loop, well, the closed loop will need to some sort of loop feedback. So I don't know if I said this previously, but the way this works is when you have a closed loop motor, you will actually pass in not PWM values. I mean, you can also, no, yeah, you don't really pass PWM values, but you pass either velocities or a distance or an angle, something like this. In our case, we will pass a velocity. And what this means, well, let's say you want the motor to rotate at a 0.5 meter per second speed, right? And so we say, well, I want the motor to be driving this speed. I want you to make the motor speed at this constant velocity. And so what it does is it measures the current velocity, it passes through a PID controller, which we will see in a bit. The PID controller basically outputs an error value, a correction value, and this correction value will be the PWM signal we will pass to the motor. And then again, it will basically just do this loop around, and it will basically accumulate errors so that we have basically a constant speed at 0.5 meters per second. And so the PWM will vary depending on how far from the set point, so the 0.5 velocity, you are. So yeah. So the condition will be then the motor modes. And in case we have the motor mode open loop, we do just this. In case we have this, we break because we don't really have anything yet. Okay. But essentially here will be a PID control. Okay. Then we send the PWM value. Okay. Now, I think this is all we need to change here. So now we get to the part where we will actually be implementing the closed loop driver. So first of all, we will need to create another constructor. And this constructor will also take in an encoder pointer. Let me include here the encoder. So it will need to include an encoder, the one we just coded. It will also need a float wheel radius, exactly. And it will also need a ticks per revolution. Okay, I think that's all we need. Yeah, ticks per revolution. Yep, that's all we need. Okay. So why do we need this? Well, first of all, the ticks per revolution will let us calculate, for example, the angle where we are within one rotation, and the radius will allow us to compute the velocity, the angular velocity, and so on, and the RPM. Okay. And basically, those are the values you will need to then compute everything else. Okay, so we can now actually print even the print status method. We will need a set velocity, and the velocity will be set, say, float. Yeah, what else do we need? Yeah, so then we need a void get motor data. And then we need to pass yeah, a reference. And then a set mode, yes. So the thing is now, a closed loop can also work as a open loop. You can switch between both, right? So yeah, set modes, mode to data. So that's that. And then we also need additional ones. So we will need a float compute RPM. Okay, we need a float, yeah, compute RPM. We need a compute velocity. We need compute angular velocity, even before, and compute distance. So let me also compute will angle. Okay. Oh, yeah. I mean, it's not necessary to have void in these method without any parameters, but it's just a nice convention, I guess, so that you know, well, we don't need to pass anything. Okay. So we have all of these: compute RPM, angular velocity, velocity distance, and we angle. Correct. I think that's all. Yeah. And then we have not a float, but a void compute motor data. Now we need something. So here we need to input the RPM. The velocity, well, we need to input the angular velocity, and the distance, nothing. Right? Yeah, okay. So more things we need here. So we have already the motor data. I don't think we need more, actually. Yeah, I think that's all. Okay. So now time to implement the rest. Actually, yeah, we'll need, well, after, we can do that after. So this, let's go here. So then void motor driver set mode. Now here, well, this can only be possible if the encoder is not a null pointer. So if it's equal to a null pointer, it's like this. Oh yeah, I need to declare this, of course. Oh boy, what is, okay, now it should be good. So if the encoder is a null pointer, it means that the mode is always this exactly. Otherwise, we can just select the mode we set. Now we have a motor driver set velocity. We don't need any of this. We need the encoder thing. But here basically we will say PID set point. Okay, we still don't have the PID, but this is what we will need to do here, okay? Yeah, exactly. Okay, so now what else? Voids, motor data. So we are passing basically a reference and we are just updating with our data, okay? Okay. Void, let me just check what I had here. Get motor data, yeah. Okay. Okay, so now print status. I will honestly just copy what I have for the print status. I think it's easier. Okay. I mean, this is not really needed, but it's nice to see yeah, some data of the motor. Print status. So on my previous one, I had it like this. Motor data score. Okay, it's not PWM, but it's PWM, like so. Okay. Cool. What else do we need? Void, motor, driver, compute. Actually, it's not this. No, yeah, compute RPM. We need a void, return type, yeah, float, motor driver, compute angular velocity, float, motor driver, compute velocity, and then, yes, okay. And then we also need a, not a float, but a void, motor driver, compute motor data. And what it does essentially is, so first of all, RPM equals compute RPM. Actually, not this, but motor data dot RPM equals that. And then motor data dot angular velocity exactly, and exactly. Okay, so now for the compute RPM, it's all we need most likely. So it's where basically all the computation will be happening. So we need to have the number of ticks we have right now. So ticks will be encoder dot get ticks. Why don't we have get ticks there? Motor encoder HPP get. Oh, why did I put a private here? I don't know. Oh yeah, it's the opposite. This one here. Okay, so get ticks. Why? Of course. Okay. So I will use auto. So auto basically just figures out what's the type. So auto now equals millis. Delta time will be now minus the last data time reading exactly. And we also need a auto dt ticks. And maybe also let me call this dt time. Okay. Yeah, that's all we need, I believe. And now we return. Let me get here the formula. So we do I see dt ticks okay, divided by delta time times, this is not what I, well, it's the same thing, but times 60 divided by ticks per revolution. Yeah. So let's put this as a 0, and here we need a float. Okay. Okay, I think, yeah. Now, if you ask me where did I got this formula, online, pretty much. And now we need to set the last encoded readings to the current ticks and the time to be now. Okay. Cool. Cool. Okay. Yeah, that's all we need. But basically, so we measure how much ticks we had from the previous time, right? And then we divide this by the ticks per revolution, kind of. And so we get the basically the angle, pretty much, you get, right? And then you just divide by the time so that we have the RPM. And so why the 60,000 means 60 seconds, 1 minute, right? RPM, rotation per minute. And we also need the delta time because we need to know what was my last computation so that everything should work. And now the RPM, the angular velocity, we just return RPM times 2 pi divided by 60. Compute velocity, return times the radius, yes. And compute the distance, we have the ticks. Now to get the distance, well, we have the wheel, right? We know the radius of the wheel. And so when you turn the wheel, right, if you take this point and you turn the wheel, actually here, you will basically make a straight line, right? And this straight line is the perimeter of the wheel. And how do you compute the perimeter? 2 pi r. So basically then, you just need to know how many ticks you have done so far, right? And you do ticks divided by ticks per revolution, you will know how many revolutions, right? How many times the wheel has turned 360 degrees so far, and then you just multiply by the perimeter, pretty much. That's the formula. Yeah. The angular, so the velocity, if you have the angular velocity, it just times the wheel radius. And the angular velocity, if you have the RPM, just RPM times 2 pi divided by 60. Okay. Yep, I think that's good. Cool. So we have now all the compute things. And where do we actually compute this? Well, we do this in the run. So here we say compute motor data. Okay. So we're still missing the PID control. That's fine. That is fine. Now we can test this actually. We can test and we should test. So to test, let's go to our main function. And now we will also pass some parameters, but before this we need to update our configuration file. So let me get my configuration file here. So if you have the same motors, you will most likely have the same values. Okay, so my wheel radius is of 33.9 centimeters, but we need meters, so 0.0339. Okay, on my case, my encoder was 490 revolution or ticks, sorry, per revolution, and this minimum PWM we don't really need it. Okay, now how do I measure this 490? Well, we can measure now. You will see. But actually, for that, I believe on the print status radians. Yes. Okay. So we need an extra thing here. So we'll have instead of it's a PWM. Then yeah, instead of this we have ticks. Then we can say, well, encoder.getTicks. Okay. So let's go again to the main now. And so we need to pass first the encoder, which we'll need to create. So encoder. Yeah, we can do encoder left, but it's not really encoder left for now. We don't really care. So motor, encoder A, motor encoder B. No? What am I missing here? Motor left. Am I missing something on the configuration? Oh, I am. I think it's the fourth one. You can check here. 4. Yep. Okay. So, and no, it doesn't need to be an interrupt pin. Okay. Main. So what was I doing? Oh yeah, it's in the encoder, sorry. So yeah, this is B. And we want to, we want to flip it. And now we just pass here the reference to be encoder. And then we need the wheel radius, and then the ticks, encoder ticks per revolution. Okay. This is all we need. And Now here we will deactivate the speed of the motor, right? And we will say motor.print status. Okay. Let me plug in the cable. Okay, so I have some problem here. What is it? Undefined motor driver. Okay, you know what? Let's do. I think it's because. Yeah, let's do it differently. Okay. So here on the setup, now we're the encoder equals new encoder. There we go. Then the same for this. Motor equals that. Encoder ticks per revolution. Okay. And now we here need to have this. Let's try again. And there's something wrong here. Undefined reference to char and sign char and sign. Oh, I see. Okay, I forgot to actually construct in the motor driver the constructor, right? Motor driver, and let's go here. uint8 pin en, uint8 pin in1, uint8 pin in2, and then encoder wheel radius, there we go. Finally. So the wheel encoder, fuel encoder will be initialized. Initializer order does not match. What is the order then? Tick, pin. The reverse is after, okay. Yeah, so this is problems with just okay. I mean, it was okay, just that since when you declare the attributes that matters for this, so that's why it was complaining. Okay. So yeah, there you go. Now it's working. Now, if you're on VS Code, you should have like a serial monitor thing, or device monitor. Then you can. Oh wait. We actually need to activate the serial thing. Protocol, or not protocol. The serial. There we go. And actually, yeah, I forgot. I mean, we need still to. Or did it complete? Init pins, motor drivers. Yep. Okay. Actually, it's okay now. Okay. So let's compile again. Okay, so now we should be having. Okay, we have this. What is this? You might ask. It's the baud rate. It's a 9600 is the baud rate. Okay. I forgot something, guys. I forgot something. Motor driver, CPP, print status. I forgot the break line here. Okay, hopefully now it's okay. So now, okay guys, so I found the problem, why it was not working. Basically I forgot here on the attach interrupt to make the spin go to the to be an interrupt pin basically. So you need to write digital pin to interrupt and then the motor pin. That was the problem basically. And I additionally changed something on the print status. I have removed the ticks here, and instead I'm just printing the encoder ticks on the loop basically. Yeah. So yeah, the way you check how many encoder ticks you need is by basically just rotating the motor at 360 degrees, more or less like this here. And yeah, as you can see, we have 492. It's more or less this. Now I advise you to have like remove the wheel or something and make like some sort of line so that we can then align it perfectly. But if you have the same motors, you should have 490. Okay, back to the development now. So once you know the configuration, once you know the revolution, ticks per revolution, sorry, and you also have the measure for the wheel radius, then we can basically just move on. Let me close here some windows. Okay, so what is next? Well, the next, and maybe I think it's the last step as well, is just to create a PID controller. Okay, now I'm not sure if it's worth it for me going through how to make a PID controller. You can use one from, yeah, you can, I mean, there are plenty of them online, but if you don't know how kind of works a PID controller, basically essentially it's this. Okay, so it will have a set point, in our case a velocity, and then we will have three different terms: the proportional, the integral, and the derivative. Now the proportional is basically just the current velocity in this case and the set point. So how far is our error to this set point? The integral, it pretty much just accumulates all the previous errors. And so if you're thinking in a graph like this one, it will basically just, let's say you have the black one, or in this, let's take the I one. Okay, so let's take the green. This is with just P, so the proportional. If you add I, it might become like the black one. Okay, it will just intensify more. And the idea is we have the P that instantly or goes as fast as possible to the set point, but it might overshoot. So we reduce a bit the P, and then we raise a bit like the I, and what it does, it just gets closer and closer to the set point. And then the D, it kind of acts like a dampener. So if you have a lot of oscillations or if it overshoots, right, you try to predict, right, where this curve is going and start to reduce before reaching the set point. Usually you only need to set up P and I. V, it's if you have a lot of D gains, it might become worse. So But yeah, these P, I, and D terms, this isn't, you will need to play around with them, okay? Now I've made my own PID controller, and I will be just adding it here real quickly, and I will be right back. All right, I have now here my PID class. So, I mean, I don't know if it's worth me going through this. Basically, this is all setters and getters, where the magic happens is in the compute method here. So here we compute the error, so from the set point to the measured value, right? Then I have here a bound, so that we always bound to this min and max output. In our case, it's minus 255 and 255. Then we compute the p term. So the p term is the constant, the gain, times the error computed. The I term is the constant or the gain, ki, times the error sum, so the previous sums. And the D term is just the error minus the previous error, okay? And also times the constant D. And then the correction is just the sum of all these P terms. These PID terms. And that's basically it, okay? There's nothing much going on here. So now to basically conclude the motor driver, what we need is we need a PID, right? So let me include here PID. So PID, yeah, PID. So that's that, and then we need to go to the constructor. Yes, I know. So we still need to initialize the PID. And the way we will do this is include configuration. Wait, it's not PID. There we go. And actually, I am wrong here. Yeah, we kind of need to initialize it here as well. And then here as well. Okay. So we are initializing with these default values, and this is because I have added them here. So these are the values I found that kind of work, but I'm still tweaking these. So it works fine when let's say you set the velocity to 0.5, for example, but then once you set the velocity to 0, there is a lot of bouncing. So I still need to tweak these values. But essentially, you just need to manually tweak these. And the way you do this is you first start with the KP and KI. You first start with KI and KD with 0, and then you start increasing the P. Once you have reached a point where it overshoots and then bounces, you divide that value by 2, and then you start increasing the I term until you are pleased with how fast it's going to the set point. And later, if you see that you have bouncing, you can add a bit of D to try to dampen this bouncing you have. This is manual tweaking. Okay. So where was I? So the PID. So now this is the PID here. Okay, so now set velocity. What we need to do is we take our PID and then we set the set point to the current velocity. Okay, that's that. And then on the run method here, we first compute the error. So error auto error equals PID compute. And what is the measured error? Well, it's the motor data dot velocity. Then we have this error, which in turn is our PWM signal from minus 255 to 255. Now we just set the PWM as our error, right? And that's basically it. The set PWM will take care of transforming to the right PWM signal, and that's pretty much it. I can double check just to be sure this is correct. Yeah, I noticed something actually. So we want to put the send PWM here. Otherwise, yeah, this kind of is useless, to be honest. You know. Yeah, let's change this. Okay, let's remove this. Let's remove this. Let's remove this. So if motor mode equals this. Okay, and then we have this here. All right. All right. I did forget something though. The set PWM must have a mode, right? So motor mode, and now we need to also go to the set PWM motor mode equals open loop by default. And so the set PWM here, we will say that set PWM modes no. So the set velocity, we also need here to say, well, the modes, motor mode is equal to closed loop, yes. And then the set PWM. Yeah, so we need to say that the mode, if it's open loop, no, if encoder equals null pointer, okay. So the set velocity. What is wrong? Set PWM here. Okay. You know what? Since we have that thing there, might as well just do set modes, motor modes, modes, And oh wait, what? We declared. Oh, we already have one here. Oh yeah, right. So we did this here already, right? So actually here we return null. Yeah, that's correct. Then this set PWM. Just need to say set mode. Okay. Why do we do this? Because then on the run, here we will say we want the motor mode to be closed loop. The reason is because since we are using set PWM for both just open loop and closed loop, we need to specify here, well, we want this to be run as a closed loop so that when you rerun this run method, it actually runs this block and not just the PWM signal. That's the reason. Okay. Yeah. That's basically it. So now to test it, we just do now, so this is already as in closed loop, and just say motor dot set velocity to be 0.5. Why do I always keep saying 0.5? Well, because in ROS we usually use the velocity as 0.5 as a default, and basically it ranges from -1 to 1, and the 0.5 is like the default velocity. Now this motor, the maximum, at least on my case, is only 0.6, the maximum you can get out of it. So yeah. And yeah, so there's one more thing we'll need to do actually. We cannot run this, let's say, as fast as it can. I mean, we could do this, but when computing this, the delta time here will be basically 0. So we will need to delay this a bit, okay? And how do we do this? Well, it's pretty easy. Now you might think that, well, okay, let's just delay, I don't know, 100 milliseconds. But if we do this, the program is actually stopped right here. This actually stops the program, and we don't really want this. We want the motors to continue moving, right? And so how can we achieve this? Well, we simply write a variable long last name, and then we have an if statement here. If last time, or actually millis minus last time is greater than, let's say, 50. We do this here, and we say that the last time is equal millis. Something like this, right? And so this way, if you have something else here running, it will not block, right? Like, okay, so for our case, it was actually okay to just have the delay, but it's not very good practice to do that, okay? Because basically, if you are using delay, you are basically just wasting CPU cycles, which is not very good. Okay, so let's push this to the board, run. Okay, so we have some errors. Oh yeah, my bad. This isn't the PID, CPP. I don't need this. And I don't need this. Okay. So it should be working. So let's see, PO device monitor. As you can see, it is always at 0.5 velocity, right? Now we can actually better see this if we use Arduino IDE. Okay. So we select the board, Arduino Nano, tuck. Now let's open this. And why is this not working? Because we need to to actually print the velocity basically. Need something else. Okay, so here we need motor data, there we go, and velocity here is 0.5. Okay, of course. There we go. Do you see this? And now this is oscillating here a bit, I mean. But it's, yeah, basically the same thing. Cool. And that's how you program a motor driver. There's one thing I want to do before finishing this video, and that is to create a timer like API to do this type of thing here. It will be easier. So HTTP, and then here a timer.cpp. Hashtag if not defined, timer HTTP. Define timer HTTP plus timer public private so here we have the timer class. We need an interval, so an unsigned long interval. We need a boolean start and a boolean auto reset, yes. Now we need a void start, a void stop, a void reset, and a boolean as elapsed. Okay. And then we can also have a void set auto reset and a void set interval. Yeah, and that's basically it. Okay, so here what we need is unsigned long interval. Last time we don't really need boolean auto reset, boolean running we don't need, and we need a unsigned long target time. Okay, includes timer, and then this timer unsigned long interval boolean start, boolean auto reset. Just use interval auto reset, and yes, does not name. What is it talking about there? Auto reset does not name a non-static data. Did you mean auto reset? Oh, of course. Yep. So if starts, you just call the start. So first of all, let's say that this is equal to true, and this is also equal to true. Now, what is this start and auto reset? So start, it will mean whenever you create an instance of the timer, it will automatically start, right, running. And the auto reset means that whenever you have reached your timer interval, it will repeat again. So if you have set to false, it basically only once, right? That's basically it. Yep. So yeah, then here, instead of start, we just reset. And now start is reset. Stop, target time equals to 0. Then reset, target time, millis. Yeah, and then we need a tag includes Arduino. And then void timer, yeah, void, boom, void timer, not void, but bool as elapsed. Let's see. We'll do this a bit different. We will account for drift. So first of all, we will take if it has elapsed, so as so elapsed, and then we will say millis greater or equal to the target time, and then if elapsed and auto resets, we will not reset, but we will take first the drift. So yeah, unsigned long drift equals the millis. Actually, yeah, let's do unsigned long now equals millis now minus target time, and we say that the target time is equal to now plus interval minus the drift, exactly. Then we just return elapsed. Okay. Yep. And now we will see that now it's very easy to make this thing here. So let's include hashtag include timer HTTP. We'll create a timer, not 1 second, but like 50 milliseconds. We'll say this is true, so we don't need to. And yeah, so now here, if timer dot as elapsed, we do this. Okay. Now we can upload this. And we can even see PO device monitor. Should be working. There we go. And now we can even check that, well, if we change this to 1 minute, 1 second, sorry. We should not do though. We should not change this to 1 second. But you will see that it will be slower. There we go. Now it's slow. Cool. Yeah, so let me change back to 50 milliseconds. Okay. And I think that's done, guys. So in this episode, we have then, where is my terminal? So in this episode, we have then developed the PID, the motor driver, right? And the purpose we are doing this way now, well, since we have two motors, now we just need two instances of this motor driver we have done so far. And in the next episode, we will be developing a motor controller. And in this motor controller, so we will be using these two motor drivers for the two motors. And basically, what it will allow us is, first of all, receive linear and angular velocities from ROS, right? So I want to go 0.5 meters per second in front, or I want to turn in 0.5 radians per second on the z-axis. And in addition, we'll be able to compute the odometry of our robot using, again, the velocity and the distances of each wheel. But that will be in the next episode. So yeah, if you have any questions, please leave a comment, give a like, subscribe if you want to see more of this type of videos. If I have missed something, if I have done something wrong or something, there's a lot of something on it, just also leave a comment and I will try to fix this as well. So yeah, see you on the next one.